video conference room. It's located downstairs in the library. To be between. Oh, sorry. Well, anyway, people who are following this on the network by the network will not be at the both session. Both session, library building, 6 to 7:30, downstairs, video conferencing room. Okay? That was for the announcement.
You can join the video conference by video conference.
Oh, so it will be live on the
live video conferencing.
Sure. Okay. Network infrastructure was, and hardware I would say, was a subject of the previous session, and now we are going to talk about network services provided by the network level somehow. At the beginning, the routing was only the only service in the end-to-end model that was designed many years ago. But clearly, more and more services are be provided by the network. I don't know if it is good for the end-to-end model. We had a discussion this morning. Anyway, this session will tackle quality of service and IPv6 and mobility. The first speaker, Victor Reijs from HEAnet. He is in charge of, I would say, the backbone, designed the backbone. He also is responsible for the next generation networking in HEAnet and has some interest in video conferences. And he is graduated from the university of 20. I think it's enough, Victor?
Yeah, okay.
Can you start?
Yeah, I'll do that. Welcome all of you. Okay, I'm Victor Reijs, working for HEAnet in Ireland. And I want to say something about QoS monitoring and service level specifications. Perhaps I'm sometimes a different view in this session. I'm not talking about how to provide quality of service in the network. That's more for instance, the BOF. I think the BOF really goes in the method how you're going to make a quality of service aware network, but I'm more looking at the user side of things, so there's a little bit different perspective, but I'm still coming back to the network. So the subjects I'm going to discuss are quality of service, what it is, or what I understand it is during this session at least. I'm talking about a little bit about measurement infrastructure, and after that there's of course time for questions. So where do I see the quality of service in this presentation? So I'm not talking about the network. I see that really as a black box, as you see there. And that network provides me some service, and the applications have to use that network. So it's more looking how the applications react on what the network provides to me. That's what I'm more interested in. And first of all, I'm also only interested in, let's say, generic applications, so FTP, voice over IP, or the simple things, HTTP. So it's not something which is a combined application like video conferencing, where you have audio and video, and if the video is bad, the audio will take over the intelligence. But so it's more looking at one application. There are other working groups working, for instance, at complex applications like in Internet 2. And the black box of the network, I leave that to Mauro and to the other people to look at that one specifically. So it's in the middle, what I'm looking at. So what is important for applications? That's what I try to find out and try to define and try to find tools for. So what are applications interested in? And it seems that applications are quite susceptible to not enough bandwidth. So if there is not enough bandwidth for video conferences, for instance, it just don't work. It doesn't work. That's simple. I see that as one of the most important ones. If you don't have enough link capacity or available bandwidth, that's the better term. So the amount of bandwidth that's available for the application, that has to be there. If not, then it doesn't work. That's simple. The other parameter which I find important, or which applications find important at least, is packet loss. I'll come back to that. But in my opinion, packet loss is the most important issue. There's quite a lot of packet loss. Voice and video don't work. FTP works, but it takes a long time to do something. So there is a trade-off, of course, rating and so on with FTP, but it's quite hampered, the performance of FTP. The other one is the one-way loss pattern. FTP doesn't look at that, but voice and video are quite susceptible to that kind of pattern, loss in the pattern. So if you have two packets which are in a different location, you have to realign them. That takes a lot of time, and most of the applications don't work, unlike video. So that is the third most important one. Delay variation is the last but not least one. Most of the applications have buffers in. You know, Real, Windows Media, and even the voice over IP have a certain buffer of a few milliseconds, so they can have the delay variation compensated. But of course, if it becomes too big, you can't compensate it, then it also will go down the drain. Perhaps people will think that the one-way delay is the one. Strange that I put it at the bottom. Why I put it at the bottom is that in my opinion, certainly in networks we are talking about, which have quite a lot of capacity, the network delay is most of the times determined by light speed. Of course, if there are routing errors and that kind of things, it's not determined by the light speed. So there's not much you can do about the delay. You just have to accept it almost, and yeah, you will see the problems when you have video conferencing and so on, that somebody is going to speak while the other one is not finished, or the other way around. Even in normal communication, that's the case sometimes, but this video conferencing can happen when somebody is very far away. So I put it as a low because I think I can't go faster than light. Perhaps I could replace all the fiber which now is in to copper, because then the delay becomes shorter, but I don't think that we want to go back to copper, so I think we are quite fixed over there. About packet loss, I said it is one of the most important, and if you have MPEG-2, for instance, and you do that over IP, remember MPEG-2 is not designed for IP networks, at least the initial IP, MPEG-2 not. So the packet loss is 10 to the minus 5 if you take just the normal MPEG-2, which is used by the broadcasters, Sky and so on, and they're using that. IP networks, the bit error rate can be quite high sometimes, certainly when you're going over commercial networks, and I think then you need the for-error correction, the FEC, and then the error rate can go as high as 10 to the minus 3, and then you get still nice video. MPEG-2 is 1.5 megabit video. So it's really dependent on the application. It's always important to define that. Some applications are much more susceptible to losses or something like that. File transfer is also quite determined by the packet loss, depending on the buffer size. I think lots of people know that the bigger the buffer size is, the less problems you have, or you can have, let's say that way. So you see here with 2 megabyte buffers, you can have 10 to the minus 6 packet loss. At that moment, the transfer of bits is 50% of what should have been, let's say, in optimal conditions. If you have a smaller buffer, which most applications do, like Windows, which is perhaps normal, I don't know, it's 10 to the minus 3. That's file transfer, and voice is not so determined on packet loss. Perhaps people would think other ways, but if you take the normal G711, which is a 64 kilobit like you are used with an ISDN, or when you have your voice over IP telephone, you can have something like 10 to the minus 1 or 10 to the minus 2 bit error loss. So it's quite tolerable to that kind of things. And there are methods like the forward error correction, where it is not so important, the packet loss. Anyway, you can even have 10% packet loss, which is quite a lot, and still understand the person. I don't say the quality is very good, but at least you can understand it, and sometimes it is more important. So that are the tools which are, or no, sorry, not the tools, but the 5 things I think we have to monitor when we want to see the quality of service a network provides. It's nice to define these tools or this metric, but then you need the tools, and that's quite a difficult problem, I think, still. There are solutions, but some are even not solved. Available bandwidth, for instance. Yeah, if you have only one link for one person available, then you know that the capacity of that link is yours, and the capacity is then also the available bandwidth. Yeah? If one person is only using that for that application. But that's normally not the case. It's always aggregated by a lot of other people, and you have to find so that, let's say, that the white space is MRTG. I don't know if people know MRTG, but that's a graph which is green at below it, and the free space is white normally. It's that which is important, because that gives you an indication what you could do with the link still. And that's called the available bandwidth. The problem is there are no tools available at this moment to measure that. They don't exist. So there are, at least people are working on it. So there is the SLOPs. I don't know what it means, but at the end of this presentation there is a list of abbreviations what it means. So, but there is a tool being developed at this moment to measure that. There are a tool, perhaps people will say a path rate. I don't know, a path rate was one made by Van Jacobsen, but that doesn't measure the available bandwidth. It only measures the bottleneck bandwidth. So that's totally different. Yeah, so what you could do is lots of MRTG pictures, see them. So look at all the interfaces of a router, check how much the load is on the interface, and then you can also find, of course, the available bandwidth end to end. But that's a little bit difficult to do, I think. So we will have to wait for that, but we are stimulating to get that tool running. The one-way packet loss, I think there are enough tools to do that. The RIPE test box will do that. There are some other tools. CRUD is one made by the people in Finland and Czech Republic, and they can measure the loss. Even a ping could do it. But the problem with the ping is that it is a two-way direction, while in principle most of the applications are only interested in one way. So you need something different. But there are tools there. That's not difficult. One-way loss pattern, it's just an internet draft. There are no tools yet available. There are some tools, but they are commercial, like HEAnet, voice over IP test tool. It's quite expensive, to be honest. It does it. It shows you how many packets are lost and in what way they are lost and so on. But there is no other free tool available to measure that, let's say that way. So we have to stimulate that to get it up also. Delay variation, there are tools for that. As you see, there are a few mentioned. At least there's a free one. The RIPE TTM box, the test box of RIPE, doesn't measure it at this moment. It has the raw data, so you can get it out of the raw data. And you can.
It does measure it.
Sorry?
It does measure it.
It does measure it? Sorry, I didn't.
Since September of last year.
Okay, sorry. It measures it. Good. So I should change it. Thanks. So there are tools enough, in my opinion, to do that. That's not a problem. One-way delay. I think there is only one tool which really does it. At least the RIPE TTM tool does it. There is a surveyor box in America. I don't know what the status about that box is, but at least there is equipment available to measure the one-way delay. The problem with one-way delay is that you have to know the times at both ends. The station where you send something and the station where you receive it. And you have to keep these clocks synchronized on both sides. And that's the difficult part. So the RIPE box does that with the GPS. So you have the GPS aerials and you point it to the air and you get a few satellites and you get precise time. It doesn't have to be precise, but at least the clocks are synchronized, and so you can measure the one-way delay. So that's the principle, but that's quite difficult, because that means that if I want to use these tools, let's say for everybody who's having video conferencing and has a problem, then I have to get a GPS over there, and that's not easy. So I'm looking also for tools which are easy to implement, let's say, on most of the platforms. So we are trying to find other tools who could do it. And as I said, RIPE, just does it. That's simple. we are now looking at, and that's being in test, at something that's based on NTP. NTP provides you the time, as you know. Both the end station and the receiving station could get the time through NTP. Only the problem is that that time is determined by the network delays in between from the primary server to that station. So you have to compensate for all that kind of jitter and so on. So there are methods of doing that, and we are looking how precise it will be, how precise a one-way delay measured based on NTP will be. Remember, most applications are not interested in a millisecond accuracy. Yeah? Perhaps the network gurus are interested in 1 millisecond delays and variations and so on, but like a voice application isn't interested in that. It could be 1 or 2 millisecond accuracy. So it is perhaps possible to use NTP, perhaps. Yeah? There is one problem, but I'll come to that later with all the other ones. So there is another tool, HEAnet, voice over IP. We tested it, and it's not usable. It just doesn't work. It's okay. Let's not go into detail. Then there is another one, IPANAMATEC. I hope I pronounced it correctly. It's a different tool. You need separate boxes for that. It's a passive measurement tool, so it's not really the tools we are looking for in this environment. But it is perhaps possible to do it, and we are going to check it. Let's say that way, just to get an idea how proprietary methods of measuring one-way delay is possible. And there is another way, that's the IPMP, that's the IP measurement protocol, and that should also be able to do some measurements on one-way delay. At least that's the principle of the tool. So together with the person who makes that tool, we are investigating how we can use it and so on. So we're working on a simple one-way delay measurement tool, because the one-way is the most important if you do, let's say, voice or file transfer and so on. The biggest problem with, certainly with the last ones, is if you have a 1 or 2 millisecond, let's say, accuracy of the one-way delay, or the one-way delay or the one-way delay jitter and so on, then that's a big error in a national network. Because most national networks only have 3 milliseconds or 1, or depending how big the country is. But it's in that range of the accuracy of the measurement method. So I think that if you want to do nationally these kind of measurements, let's say you want to measure the one-way delay, that you are almost stuck with something that's based on GPS. You can use this kind of simple tools perhaps when you do it over international links or European links, let's say, where the delays are 20 milliseconds or 100 milliseconds to America. I think then the tool based on NTP is usable, but I don't think that it could be usable nationally. Certainly when you go to 2.4 gigabit links, then countries are quite, there are 3 milliseconds. At least the Netherlands is 3 milliseconds. I think Ireland is 6 milliseconds at this moment with the speed. So there is an issue there. So I think we still have to go to that GPS perhaps, which would be a pity because it's not that expensive anymore, but it is difficult to get at an end user side. So all the tools I mentioned were the ones just looking at one thing, one-way delay, packet loss and so on, but there are tools who are looking at composite metrics. Like for video, it's not only the delay which is important, but it is a combination of delay and packet loss and so on. And so there are a few tools that can handle that kind of things together, and they gave a score how good the IP connection is for these tools. And there is at least one for audio available. You see the standards there, and there are implementations available. The first one is quite expensive, again. The second one is just a public one. But it is looking passively at streams already existing. But it doesn't have to be a problem. And for video, there is no standard yet. How to score a video stream or an MPEG stream 2 or an MPEG stream 4 or something else. So something has to be done there. And certainly there are no tools looking at the network side. There are perhaps tools that if you see the picture and you see many pixels wrong, then they gave a score. But it is not related to the network metric of loss and that kind of things. It's more related to what you see. And that's not something which you can do. Yeah. And I think there are a lot of tools being made in the grid environment, so and also working on that. Okay, back to, so that are the tools. I think then we have to go to measurement infrastructure. How do we measure this on a national and European and global scale? Because it's nice to measure this kind of things locally or nationally, but you have to do it on a bigger scale, I think. So I have a few issues we have to tackle for doing that. And I think we have to have a flexible platform where these things are going to run on. Because some people have Linux, other people have Windows, others have, and a Cisco is also a box, of course, where you want to do this kind of tests too. So you need a flexible platform for all this kind of tools to be able to be implemented in that kind of stuff. It has to be used for end users. Yeah, I want to test my video conferencing, but as a network manager, it's not in my daytime job. I also want to be able to use it, and perhaps with a better accuracy, that indeed can always use the GPS for one-way delay. So there is difference in accuracies and needs. This platform has to look at. Different measurements. Most of the measurements are active, what I said. One-way delay was always measured by sending a packet one way and getting it out on the other side and measuring the time. This is an active measurement. Passive is also quite important in this environment. Sometimes you already have the stream, so why not use that stream to measure the things? It has to be upgradable. Tests we now know at this moment are perhaps not needed next year anymore, or we invent new ones or better ones and so on. So we must be able to put this kind of things in these end stations and at these measurement points and so on to be able to measure it. So there is a moving and evolving environment. It has to be secure. It should not be DOS attack on routers or end stations and so on. So you need something on secure access and how to do that. There are some ideas about it. There is a network where you have to use PKI standards to get access to this kind of measurements and so on, or to do a measurement. Multiple management domains, yeah. It's every country in Europe has to be taking part in this, and you have to get the information also between each other. You have to use information somebody else perhaps have gotten already. You want to reuse that perhaps. Yeah. Another thing is you need to do resource management. Workstation could be so busy with doing a test that it can't do another test anymore. It should be perhaps being so busy with doing something else that it can't do a test. So you have to do resource management on these stations. So you have to look at that kind of things when you do this kind of measurements. You can't. Yeah, you could install everywhere a single PC to do this kind of measurement, but it will be quite expensive for an end-to-end scheme. This is a little bit the method, I think. Yeah, I'm not going into detail, but there are multiple domains, multiple stations where you want to put the equipment and where you want to test to. You want not only to test end-to-end, but if you see there are a problem, you also want to test from here, for instance, to that router, or to another system or something like this, to see and debug the path. Yeah? I think that's it. So the tools, the metric, the tools, and the infrastructure, I think, are quite important to get in. And there are quite a lot of people working on it. The grids are quite working on it, I think. We get an example, certainly, in the next speaker. We'll talk about measurement infrastructure. So, but there's a lot to be done to get it open and secure and so on, I think. Are there questions?
Thank you, Victor. We have time for 1, 2, 3 questions. Questions, please? No question? Question for me. What kind of tools are you using as a manager or in HEAnet?
I think the ones at this moment, the one I use is ThinkPlotter, which is a nice one where you can see it's almost like a trace route. But it gives a graphical representation of the delay, but it also prints in a nice column the packet loss, and that way you can relate delay, packet loss, where the packet loss starts in the whole link, and it gives me a good idea. Okay, that could be a problem. Yeah, it's not a solution always, but at least it gives you an indication where the problem is. And yeah, for HEAnet, I also use sometimes for video conferencing and so on. But that's a commercial project and it's quite expensive.
But you use it at national level, you don't use it on international lines?
No, both I use.
You are faced with inter-domain.
No, HEAnet has a nice idea. You download an endpoint on whatever system, except routers, but at least some 5 operating systems. You can just do file transfers and scripting between these 2 endpoints and measure delays and loss and so on.
Question.
Being accused to be the author of black box, I still think that one of the problems is how to relate black box measurements to application measurements.
Yeah.
I mean, I see a gap between these 2 worlds.
Yeah.
And so, what is the way to solve the problem in debugging at the same time application QoS and network QoS? Discuss it that way. I think it's worthwhile commenting.
I think you should try to separate them. I'm a layered man, let's say it that way, in some way. I think that there are applications are looking at these errors or this kind of metric, and there are also let's say for video you know the composite things, yeah, you know the quality. I think that we need to first of all we need a translation between the metric I talked about and how an application behaves. So that's the behavior. If the packet loss goes up, an application doesn't work, but you need to know that function. Yeah? And the other thing is, I think that the black box people, let's say the network management people or the network managers, have to know that if they fiddle around with the queue depth or the priority and so on, how that influences this metric. And I think they have to study that. So I would like to get from the network people that they know that if they fiddle around with this parameter, that will have this behavior on these 5 issues. And so I have let's say an interface defined for quality of service at that level. And the application people have exactly to do the same. They also have to know that if the network changes, how does my application change? I think they have to change perhaps their application to have a better behavior at looking at network. Most applications are written for local area networks. And they don't work on wide area networks. So there is an issue there also.
I think the human interfaces.
Yeah. But the MOS, for instance, is a human interface. It determines how a user would see the performance of that application. Let's see the one for voice you have available. I think for FTP it's simple 50% of the time. If you have to wait 2 times longer for getting a file, for me that's bad.
I suggest that we go. Oh, sorry. One last question.
I know that Matt Sevasti was looking at an alternative to getting a real GPS signal, tapping cell phone things for timing. Do you happen to know how that turned out?
Oh, perhaps we should also put that on our test list. We didn't do that. Sorry. No. I don't know how accurate that will be. Yeah, Henk?
There is a CDMA module available in the US, which gives you timestamp similar to what you can get from the GPS. We haven't played with it yet. If you look at the specs, it's sort of the same accuracy that you can get. Of course, you rely on the fact that you have CDMA in network, so it won't work here in Europe.
Right. So I think it's fully dependent on CDMA. I mean, there's timing signals at the cell phone things, generally depending on which system you use, right? It's there. But the issue for them was they had a lot of trouble getting permission to, drill a hole in the roof of a pop or whatever. Whereas sometimes that signal might have cell phone access of some kind.
Yeah, indeed. Yeah, no, in that sense, perhaps it's okay.
Okay.
Thanks.
Thank you, Victor.
Yeah.
Again.
Where to put it in? I'll just hold it.
From the university.
Yeah, this one, yes.
University, of Patras in Greece. She is currently a PhD candidate at the same department in same university, research and development engineer for GRNET, which is a Greek national network. and Computer Technology Institute in Greece. The presentation will be on SEQUIN status report. Is it correct?
Yes.
Yes? Okay, so Afrodite.
Okay, so good afternoon from me. I will try to present to you the work that SEQUIN has done throughout its duration and mainly in the last year of its operation. As many of you might know, SEQUIN was an IST project that started in November 2000 and ended in last April. Partners were, apart from Dante, 7 NRNs from 7 different European countries, from Germany, Italy, Greece, Poland, France, Switzerland, and Great Britain. And most of the project's public results can be found in the project website. To give you a brief overview of what has SEQUIN achieved was, first of all, to define and implement an end-to-end quality of service model approach, operating across multiple management domains and based on the IP protocol. And okay, it was supposed to be different. It's not only ATM technology, but is on a diverse set of different link layer technologies. The project has focused mainly on the implementation for the premium IP service, which has already been mentioned in some sessions today, and mainly aims at providing the equivalent of a virtual list line between two end users. The architecture and most of the work I will talk about today was initially targeted at the GRNET, the Pan-European Gigabit Research Network, and is applicable mainly to the national research and education networks across Europe and all the local DIFSERV domains attached to these NRNs. The quality of service parameters that SEQUIN focused on are the ones that were already presented in the previous presentation, except for lost pattern. And I will not get into much detail about them since they have already been discussed. SEQUIN in the first year distributed a series of questionnaires to end users in order to get a feeling of what their quality of service expectations were. And after analyzing the first matrix that was a result of processing the questionnaire answers that we got, we ended up with 3 different types of quality of service levels. Apart from the best effort one, we also had premium IP, which was a service of very good quality, very small, negligible packet loss mainly, small jitter, small one-way delay, and also IP Plus, which was another type of service that could be set up with a milder quality of service expectations than premium IP, but also some guarantees. So SEQUIN, as I already said, focused on premium IP. Premium IP was built according to the DIFSERV EF per whole behavior. Some basic principles for its deployment were over-provisioning, limiting the percentage of capacity that was devoted to IP premium to 5% of links, to use static provisioning and the minimal number of actions per network node in order to ease the implementation, to adopt a modular approach, meaning that in a series of interconnected domains, each domain was free to adapt the IP premium service in a different time scale than the rest of the domains, and also a model that could be implemented using some already existing tools. Of course, since premium IP is based on IP, it's independent of the transport protocol, and as a last step in its implementation, a chain of premium IP compatible per domain behaviors were required. The tasks for each node in a domain in order to implement premium IP were divided into compulsory ones and not compulsory ones. Very important tasks are admission control and classification, as well as scheduling, with a very strict priority, which should always be performed in each node of a IP Premium-enabled domain. We also advise marking in selected locations, policing, again, in selected locations in the ingress, mainly, of each domain. Shaping is not necessary in the IP Premium model. Congestion control is also not necessary. And on selected locations, quality of service rules and monitoring and accounting are suggested. So the Premium IP specification was based on two general rules, that packets would be classified and scheduled with high priority based on their DSCP value on all nodes of an IP Premium providing domain, and also that IP Premium traffic is not polished as it exits domains, and it's not shaped anywhere in the path from one end user to the other. So in order to follow the way from one end user to the other, we can say that in the first domain where the end user is attached, packets, in order to implement Premium IP, should be classified according to the IP pair prefixes, and they should be strictly polished and marked according to the IP Premium capacity that is devoted to this specific user. In all other interfaces, as the packets cross consecutive domains, and mainly in the ingress of a backbone domain, packets are polished in an aggregated way. For the case of GRNET, it was advised to follow an aggregation by domain source and destination, by NRN source and NRN destination. And in that way, the SLAs that would be created between GRNET and all the NRNs attached to GRNET will contain the matrices of couples of packet aggregates transferred from one NRN to another. And as you can see from this figure, policing can be avoided at the egress of NRNs receiving traffic from a trusted backbone such as GRNET. Here's another example which mainly repeats this functionality. What is visible from this figure is how a domain such as domain 2, which is an ATM domain, can provide the IP Premium per domain behavior by providing a dedicated PVC to the traffic, to the IP Premium traffic that crosses this domain. As for the rest, the rules that I already described apply. Here we can see how using the highest priority queuing mechanism and limiting premium capacity to a small percentage of the backbone links allows us to exploit the available bandwidth in the profit of premium traffic. And how does that ensure that some part of the link bandwidth is devoted to premium traffic? In order to prove and to test the implementation of IP Premium, a proof of concept testbed was set up. The goals for this proof of concept testbed was, first of all, to have access to a control environment composed by diverse technologies, and also to verify the functionality of Premium IP required by each of the components involved. The tests performed started from laboratory tests for basic router functionality, tests in the wide area to make sure that the interaction and between the different network technologies did not cause major problems, and also, and most importantly, tests involving end users to verify the provisioning process for Premium IP. So a major part of our tests were performed with H323 users, which came from the TF Stream task force. A few details are provided here concerning the technologies over which these tests and the links and the topology over these tests were carried out. Tests were carried out both with and without premium IP, and the users were asked to subjectively provide feedback on the quality perceived. And also SEQUIN performed some objective measurements with certain tools to assess the quality of the premium IP implementation. Here's very briefly the topology that were used. You can see that there are a number of different link layer technologies involved, and the topology, which is not trivial, it involves 5 endpoints interconnected through the GRNET network. So the test scenarios were performed with the use of some simple measurement tools that were first of all used. First of all, we had to use these tools to verify that end-to-end setup was successful. Then we had some real video, H323 video conference taking place, and the users were asked to subjectively provide their opinion on how the service works and how good quality they perceive. We used ping to measure end-to-end RTT, and then we simulated the video conference traffic pattern with the use of the RUD and CRUD tool in order to measure jitter and packet loss. Finally, without any other traffic involved, we used NetPerf to measure the throughput that was achieved between end users. Here is a kind of not very easily analyzed matrices of results. These are actually the grades that end users gave according to the quality they perceived, both in audio and in video, when IP Premium was enabled for the video conferencing. There's not much to say about that, and it's rather subjective, so I will move on to the more objective results. These are indicative measurements that were carried out as far as the bandwidth in the first matrix, RTT in the second one, and packet loss in percentage in the third matrix when IP Premium was enabled for these tests. We can see some very good, as a green color denotes results. There were some red points that were caused some concern, but it's not, we don't have the time to analyze them at the moment. In general, we can say that IP Premium provided us with good quality, and this is mainly, this is better shown in these two graphs, which provide jitter measurements for the same tests. The first one presents how jitter was distributed, the green color with premium IP traffic and the red color with best effort traffic, and we can see a significant improvement in reducing the jitter values. And also the second figure shows the average jitter versus the packet size in both cases. We can see here how much improvement there has been with the introduction of premium IP. Another very, very important part of the testing carried within SEQUIN is that of real cases of IST projects. One of them involved IST project Aquila, and the other one, the project Moican. Actually, the first one, both of them started, both of these testing phases started towards the end of SEQUIN, and Aquila is at this moment the one that has made most results, and Moican is also in the progress at the moment. We hope to have some results real soon about the IP Premium implementation in these cases. SEQUIN, towards its end, also dealt with some issues such as monitoring. We considered different alternatives for monitoring, from measuring IP Premium quality in the end-to-end path, as the first figure shows, from measurements that involved end-to-end interdomain points and connection paths between domains, and also in the third alternative, the alternative of stage 2 to which intra-domain measurements between routers were added. At the moment, although SEQUIN was not able to provide a full monitoring infrastructure before it ended, we were most in favor of the second alternative. We also made some comparison between simple management tools that we used in the H323 tests, such as ping and root crude, and some commercial products, such as the RIPE test boxes. And here is a brief listing of their advantages and disadvantages. And part of SEQUIN's work was an SLAs as a definition of, as a means to control and deliver the quality of service of premium IP, as well as the establishment of end-to-end IP connectivity. Of course, SEQUIN used unidirectional SLAs, and these SLAs were initially defined between GRNET and the NRNs. And as I mentioned earlier, such SLAs involved a matrix for NRN to NRN traffic connectivity employing the IP premium service. Here is very briefly the proposed SLA template that was used. I would like to explicitly mention the traffic envelope and traffic conformance part, which was the token bucket policing mechanism with a depth that was depending on the number of router interfaces on the same router or the part of the service and the distance from the source, and a rate that was 1.5 times the available or the guaranteed for IP premium bandwidth. Some work was also done on describing end-to-end SLAs within for the IP premium implementation, and the need to have some verification mechanism for end users in order to make sure that by using an end-to-end SLA, in order to make sure that when the individual SLAs between adjacent domains were combined, the result that the end users would get would be satisfactory. And SEQUIN has thought of the use of simple measurement tools as a means for end users to verify this end-to-end IP premium connectivity. A few words about the service provisioning model that SEQUIN tried to adopt. We thought of using a centralized provisioning model, appointing a service provision coordinator for each IP premium connection between two end users, and have on the left side the technical people talking to each other, and on the right side the end users and the performance evaluator people to talk to each other, and these people would be coordinated by a person who would give feedback from the end users in cases that quality perceived was not satisfactory to the technical persons and vice versa. However, in the test phases that were carried out, it turned out that since parameters and configuration for premium IP are not yet state-of-the-art, a more collaborative approach was needed for these tests, and a lot of collaboration and exchange of information between all involved parties without having a central authority organizing the whole procedure was necessary. So, very briefly, the conclusions were that SEQUIN has shown how to deploy premium IP, and the H323 testing phase, and most importantly, the tests that were the setup of premium IP on the backbone of GRNET in order to be used by two IST projects, demonstrate the feasibility of deploying premium IP. NRNs are now invited to implement it. The service provisioning model needs further elaboration, and it's also necessary very shortly to define and make more stable a measurement architecture and the measurement tools to verify the provisioning of the service. Also, there are some thoughts of premium IP being the replacement of ATM-based management of bandwidth. Thank you.
Thank you. We have plenty of time for questions. Questions from the floor? Yeah.
I'm not expert about QoS, and I ask, how did you limit the bandwidth of premium EP over the bandwidth of normal of best effort?
Okay, so this was the task that was delegated to policing, actually. So policing, both in the ingress of the backbone network, in our case GRNET, and also in NRN networks, was configured in a very strict way. For example, in the H323 testing, we had, I think, 2 megabits per interface policing in order to make sure that the bandwidth of a premium IP would never exceed some percentage of the link.
In the input,
Yes.
we limit the premium traffic,
Yes.
and in the backbone,
Okay.
we have the priority.
Yes.
Okay.
Could I ask about the subjective results you got? Did you find any correlation between those and your more objective measurements, or did you think your objective measurements were consistent in any way with what the users found subjectively?
We think so, yes. I think that if we take a look back at the subjective results, we can see a very good quality as far as video is concerned. It would be better maybe to have subjective results for best effort service in order to compare them. But generally, apart from some individual cases in the audio performance, generally end users were satisfied by what they were seeing and hearing.
Before you, Mauro, can I? Yes. Just to carry on this question, not to be provocative, but I'll ask, where were the users located? Were they on the last mile bandwidth limitation line, or were they on NRNs? Because one point in your conclusion is we encourage NRNs to implement quality of service. Yes, but in some countries, NRN are only the backbone. And the backbone connect directly large campuses. But a lot of smaller campuses have to go through other domains to access the backbone. So there is the problem, you see?
For the H323 testing phase, I think, which is depicted here, end users were as close to the real end as we could. What is taking place now in the rest of testing with the IST projects is even better in respect to what you have already explained. End users, in this case, in these 2 projects, are really, really at the end. They're in university campuses, in less privileged ends than the ends that we used in H323 testing. So we're just awaiting for these results.
Yeah, I just wanted to add a comment which is relative also to what you said. Some of those red results were in the cases in which not exactly all the path were completely according to the AP premium model. For example, there were some links which were over-provisioned but not really high queuing, with a high priority queuing enabled. And so take these as really a draft of the first measurements, because as you can see from the plot of the geography of the test was very complex. There were at least 30 or 50 links involved, and the users were on the lines actually. So the moral from that is it is true. It's not so easy to extend the model up to the users, but of course the good thing about that is that it's relatively easy to deploy on the core backbone and then extend step by step. It does not need to be done at the same time, everything at the same time. You may start and then go on.
Thank you. Step by step.
Okay. It's related to the subjective part. You can measure the subjective part, objective in some way, by using the MOS I explained. The people really experience. Are you going to do that with the test so that you have let's say, such an objective test method for the subjective experience of people?
Do you mean in the testing phase that is now in progress?
Yeah, because it would be very nice to know if it maps in some way with because that are tools which are available for H323. And see how it maps on the results you see in the network.
Yeah, SEQUIN has ended already.
Okay, yeah.
So
the next phase.
Yes, maybe yes. That would be useful. Yes.
They will. Good.
Both of them, for example, are using telemetry, right?
Yeah.
And so I think that both doesn't work. So
It would be great.
So I think that more measurements will come out from those according to these kinds. But actually, subjective measurements are very difficult.
There is a relation between subjective ones and the MOS that's already tested for 20 years or 30 years. So.
You can carry on your debate, but there is a buff in 30 minutes, okay? So it's the next step. SEQUIN is finished. Thank you again, Aphrodite. Well, now we are going to switch to something else, perhaps. Not quality of service, but something that can ease or facilitate the life of user. Speech will be given by Andrew Scott. He is a senior lecturer at Lancaster University in the UK. He's working on IPv6 and mobility. And his talk will describe some of the past projects he worked on mobile and wireless system. And of course, the new mobile IPv6 test. Okay, Andrew.
Thank you. Well, first of all, I thought I'd say just a little bit about where Lancaster actually is, because few people seem to know. That's actually from the UK. We're actually about in the middle, as you can see. And you'll see from the pictures the sort of countryside that's round about, and you'll see that that's actually quite important for some of the networks we've been involved in. So it's very hilly, there's a lot of water, and so on, which has some interesting issues for wireless networks. Going back quite a few years now, the early 90s, we started getting involved in doing point-to-point wireless links. It seemed a good idea to avoid paying telephone charges, so we'd have a good play around with those sorts of things and see what happened. And then actually our sister department got interested in actually using these sorts of technologies to interconnect schools, because schools don't tend to like paying recurrent charges. They don't mind actually paying up front, possibly quite a large amount of money. But as soon as you actually say you're going to have to pay usage charges, they say, well, we don't know how many people are going to use it, we don't know how many hours people are going to spend on the system and so on. So we thought we'd actually look at some commercial wireless technologies. And this was about the time that Waveland was picking up. So we actually used some early commercial kit that had very high gain receive antennas and allowed us to actually extend the range of Waveland out over the city and the surrounding areas. We actually connected the schools in that way. To go further, we actually used some sort of fairly standard telecoms sort of kit. You can see the sort of 13 and 23 gig links that we could actually put up. And they would actually typically get us about 16 kilometers or something like that away from the main site quite easily. Well, because we'd had so much success with that and people were quite interested, the system worked, we thought we'd actually go a bit further. And there was a lot of interest coming out from the government in connecting schools across a wider area. So we ended up actually covering the whole of Lancashire and Cumbria. And we've actually used, besides regular links, we've used things like DSL, commercial SDH links and so on. So whatever we can pick up to develop the technology and actually bring the schools together. So as you can see there, we're essentially getting the task of about 1,000 primary schools and 131 secondary schools. So that area, if you actually look at it, is about 177 kilometres by 97 kilometres. I say there's a lot of radio links in there as well, and a lot of hills and water to go over. Well, that's an interesting platform that we could start to think about for playing with mobile networking. Just to actually give you a hint of some of the things we've actually done over the years in mobile systems, and really sort of setting the groundwork for this testbed we're going to actually start talking about. A whole host of different things, a lot of interest in mobile IPv6, a lot of interest in actually developing context-aware applications, and applications that can change the quality of service that they're actually getting or demanding from the network, depending on the particular network characteristics. So one of the first things we did was the sort of typical tourist application. One of the unusual things about this, we actually used wireless LAN cells to actually provide the context. So as you actually walked up to a building, you'd actually enter a wireless LAN cell and you'd actually get information about those sorts of attractions. So that was one of our sort of first applications that we actually played around with mobile systems. And as with many of these things, the simplest applications turn out to be the most fun and sort of interesting. Another sort of application that we tried, not necessarily looking at networking in the sort of traditional sense, but picking up on the sort of mobility aspect. We had a conference that was actually running at a site about 10 miles south of the university, and we decided we'd actually put a little travel portal. And the idea was that we'd actually run tour buses that were going up to the railway station, picking people up and bringing them back to the university and also the conference centre. So we actually used GPS, we actually linked this into an iPack, and we had a whole host of maps of the area, all different sort of scales and so on. And we'd actually dynamically change the scales and all these sorts of things that you wanted about in the tour bus. Quite interesting that just after we actually built this, we found a commercial company had actually picked up on a similar idea. And we actually used to highlight things like speed cameras. So as you're wandering around in the bus, it would actually say you were just about to approach a speed camera, tell you the speed and all these sorts of things. And we also had the idea that as you moved up to a particular area, say the hotel, you could actually download MP3 files that people had actually requested and it would actually play on the bus as you were going along. So all sorts of fun little things. The actual communication was actually using SMS. At the time, we didn't have GPS and GPRS technology. It was something that was expensive. You didn't really have cards that allowed you to actually provide GPRS connections. So we just used standard sort of text messages. So getting towards sort of looking at these as sort of things we can pick up on and go further into developing sort of more sophisticated things. We did quite a lot of work with mobile IPv6. We actually built one of the first Linux implementations of mobile IPv6, and we believe it was the first kernel version. And that actually developed a lot of interest, and we actually were approached by Cisco and Microsoft, and we actually implemented mobile IPv6 for Cisco iOS. We've now got that running on things like ADSL boxes, SDSL boxes, and so on, as well as the sort of full range of iOS routers. And working with Microsoft, we've actually ported to all the different versions of the Microsoft operating systems, including the ones that are due for release in the next few months. So we can actually run mobile IP across the full range of sort of situations that you might actually want in a network. Just to actually show that this thing does actually work in some sense, we have some pictures of a demo that was run in Seattle. or Redmond. You can actually see one of the web pads on the left. That's basically a C box that's running mobile IPv6. And over here we've actually got a version of Microsoft Exchange, Microsoft Outlook, where you probably can't quite see the sort of Ethernet connections being actually removed, and we've actually got a wireless LAN card we just plugged in, and the whole thing actually keeps going. So that's a seamless handover. So these things do actually work, and they are available, at least on the research labs, to actually develop and so on. Taking this further again, we've actually got a piece of middleware that we've been using for a few years now, which actually sits on top of mobile IPv6 and allows you to actually drag and drop network connections. So literally, if you've got a particular application that's actually running a stream to a media server or something, if you're actually going to move on to a different network, or you've got a different network that becomes available, you can literally, just through an interface, drag individual connections, individual streams, and choose which network interface you want them to go out of. And that's seamless. The application doesn't know anything about that. So that actually opens up all sorts of nice little ways of applications handling different types of network handovers and different sort of networks becoming available or sort of disappearing as time progresses. So the sort of remaining part of the talk is, as I said, looking towards building on those sorts of things. And we've got a testbed that's been set up at Lancaster. It's funded by Cisco, Microsoft and Orange. And essentially we're looking at the different areas that you might actually start to use mobility. It's a sort of a new type of application sort of generated, if you like. So we think about the home. People clearly don't just work in the office all the time. They actually go home. They want to do things around the house. Getting access to sort of information, whether it's entertainment or whether it's actually connecting back to something like an office, is really quite important. So being able to actually get mobility at that level is something that we're actually looking at. So as you'll see, we've got a lot of connections to homes being installed at the moment. Around the surrounding area, we're actually looking at providing connectivity to things like shops, parks, and all these sorts of things, so that you can actually, again, if you're actually going to the shops, you can actually pick up information about possibly the state of something in your house or something like that. And finally, the other area that we want to look at is the workplace. So, as many people sort of install wireless LANs around their offices and so on. This is a typical building that you might install that in. We want to look at those sorts of things and see how all those different types of environments come together. So we have this idea that we have some sort of core infrastructure with the university campus, the city, various partner sites, and also sort of a test lab where we can actually trial applications before we push them out into the main network. So just to actually give you a little bit of context, the university is about 1 kilometre long by about 500 metres wide. So bear that in mind. That's actually quite an interesting pair of figures, as we'll see later on. Looking at the campus, one of the first things that we had to do was decide what sort of coverage we wanted and how to actually go about getting that coverage. So we want to include all the things like the coffee bars, the restaurants, the lecture theatres. Those are clearly places where people actually congregate and actually want to use mobile for the system. Clearly departments are important, but they tend to have their own pots of money. So unless there's a need to actually bring a particular department on, that would be something we'd expect the department to do or the university rather than the project itself. Having said that, the computing department, and as we'll see, part of a campus hotel that's actually on site, has actually been covered by the project to actually develop that into a more sort of interesting environment. So looking at the particular types of technologies, there are a whole host of different types of antennas that we can actually use that have very different characteristics as far as coverage. And the ones we tend to have actually used are ones that give about 80 degrees of coverage. So if we look at the southern half of the campus, you can actually see the sort of range of departments that are actually residing in that particular area. You can also see that by using just 8 base stations, we can actually get 11 megabits of coverage throughout the whole of the central walkway in the university. And then we obviously infill around the departments as well. So you actually don't need quite as much kit as you might imagine to actually do these sorts of things. So there's very few places there that are dropping to 5 megabits. We actually compare that to an indoor system. This is the Management Development Centre that I was talking about. They've actually got 4 base stations covering the sort of innards of that building. So going outside, getting wide area coverage isn't necessarily as difficult as it might look. In terms of residential networking, trying to bring people on board that are working from home or whatever, it's very difficult now to actually compete with ADSL. If you actually reside in an area that's got an exchange that's been upgraded, then ADSL actually works out quite cheap. And unless you actually want to pay quite a significant increase in money to actually get the extra bandwidth, there's very little point in actually going further. Having said that, if you actually get a large cluster of houses, you can actually use something like SDSL as a feed, and then use that to actually select a group of houses, put some omnidirectional antennas in, a few other antennas, and then you can get a blanket coverage of the area. So this is a particular housing estate that's just south of Lancaster that we're involved in covering at the moment. Looking at the city itself, remember the figures that I talked about for the size of the university, about 1 kilometre long by 500 metres. That's about the same size as the actual city of Lancaster itself. Now there's a lot more clutter in the actual city centre, but you can see that the same sorts of numbers of base stations should be able to cover the core of the city centre itself, and that's one of the areas that we're actually currently looking at the moment. One of the nice things about Lancaster as well is the fact that a large percentage of the population is actually based at the university. So in other words, a lot of our own staff and students are actually residing in the city centre itself. So that's a plus point. We've got a nice group of users that we can actually experiment with and so on. Another nice feature of the testbed is that because we've got a link to Orange are looking at providing us with a direct physical connection to their testbed, which will actually allow us to wander around Lancaster and actually be on the Orange test network, which means that we can actually play around with things like GPRS much more easily, or possibly something like 3G, depending on when that becomes available. Looking towards some of the things we're actually doing on the testbed as well as just getting coverage, now the first thing that you actually start to look at is security. There's all these reports about people wandering around with Pringles tubes and so on. You want to actually find some way of actually removing the ability for just random people to join into your core network. So one of the things we're actually doing is using the actual functionality of IPv6, the actual extension headers, to allow us to insert tokens that can actually be checked by routers as the packets go into the core of the network. And because we're looking at a mobile environment, essentially what we do when a machine has been authenticated, then the access control lists of not only the router that you're actually on at the moment, but adjacent routers are actually updated as well. And that means that when you do actually move into a new area, then you don't actually see a break in connectivity. So the access lists are already primed. It's actually very similar to the sort of early versions of Kerberos and so on. So it's relatively lightweight because you should be looking at other types of security anyway for actually protecting the network itself. Another sort of application that we're looking at is content delivery, looking at delivering different types of streams across different types of networks, and also actually looking towards actual proper content delivery networks. The sort of things that we've got at the moment with caching and so on work very well if you've just got HTML pages coming down. If you've got video, that doesn't tend to work very well, particularly if you're actually moving around. So one of the things we were actually doing a few years ago was a project called Cogent, and we're actually looking now to drive this with IPv6, essentially what you have is a set of media servers that are holding different formats of videos. And as you actually move around the network, based on things like signal to noise ratio, particular network connections that you've got available, the actual scheduler will actually change the different media types that are being sent around the network, so that as you move from one network to another, the encoding of the video and audio will actually change dynamically. So hopefully you'll get the best type of service for the particular network that you're on. One of the things that you can actually do, and we use quite heavily in Cogent, is if you look at something like H.263 as an example of a media type, if you're actually currently watching an MPEG stream, if the system thinks that you're likely to move onto a low bandwidth network fairly soon, it can actually piggyback some of the H.263 data within the MPEG stream. And that means that when you actually move over onto a low bandwidth network, all the buffers and so on in your device are actually primed and ready for the handover. So there's all sorts of little games that you can start to play like that to get these things to work. And it's predominantly a multicast system. So that's just telling you about the session manager and how it brokers the requests. All sorts of other work that we're actually doing at the moment. We've got ad hoc networking, active networking, and one of the things that the guys are getting quite excited about at the moment is actually providing mobile games. So they've got visions of school children running around the local parks with iPads and so on. And that's the latest idea. So, if you want to know more, the slides are on the web, and also there's a number of links there that you can actually go to get more information about the different types of work we're doing.
Thank you. Plenty of time. Questions?
Can you say more about this user authorization? Well, you didn't put much stress on it, so probably there is not a big need for it in your network at the moment, but we are all concerned about others using our networks for purposes we never thought of.
It is an important aspect of the network. Clearly, you've got a wireless LAN in this sort of environment. You've got some degree of knowledge that the people in the building are likely to be people that should be having access to your network. If you're actually going further and looking towards the sorts of environments we're looking at in Testbed, where you may be deploying this around a city centre or something like that, then clearly you've no idea who could actually be in that area. So it's quite important that you have some sort of way of determining who has access to your main network. We're not particularly concerned about people with this system actually using resources that are within one cell. It's the actual area beyond that that we're particularly interested in. So essentially what you do, you have a router that has an access list. It allows connections just to an authentication server, and the machine that you're actually using will send a packet to an authentication server. That will, based on your addresses, say yes or no to the particular request. If the request is successful, you'll be given a token, which has a small lifetime, and the information about your machine will actually be inserted into the access list of the routers nearby. Periodically, because the token expires, you've actually got to re-authenticate. And that obviously just means that if someone steals a token, then they can't actually use the network for any length of time. So it's a lightweight solution because this should be supported by things that protect the servers. I mean, you should be using things like Kerberos to protect your servers. But this actually just tries to prevent people getting unauthorized access to the network.
And what mechanism you use to authenticate?
It's basically the IP address that we actually use. And because the IP address is actually dynamic, then you can actually use that. So it's a lightweight system.
Still IP is not giving you information about who's the user.
But you've actually got within mobile IPv6 the range of addresses based on your home address. You've got your local addresses, your link local addresses, and so on. So you can actually use those to determine who somebody is to some extent. So it's not intended to be a very secure system. So.
Question? Yeah. Just take some.
How many users are using this network at the moment?
At the moment, very few. We're essentially just rolling out the core of the network. One of the problems, obviously, because we're actually building this from scratch, you need quite a large amount of infrastructure to go in before real users can actually start on the system. So at the moment, we've just got probably about 10 users, something like that. Now, what we're going to do next is actually bring on blocks of students, blocks of university staff to actually use the network and trial it.
Any other question?
Do you have any propagation problems with regards to when users move inside buildings or so forth? How do you get around
If
that?
you actually move into a building, then you would have internal wavelength cells that are covering that. And mobile IPv6 allows seamless handoffs between different networks. So the applications don't actually see that you actually moved from one network to another network.
So you'd have cells inside the building?
Yeah.
What kind of encryption are you using?
Encryption in terms of protecting data, none. That's up to the user, that's up to whatever policies a department wishes to enforce. The only encryption that we're actually have on this is encrypting the tokens. So that's all we're interested in as far as the infrastructure is concerned.
No other question? I may have one. You said that it's possible to have non-disruptive session between the mobile and system and, let's say, a video server, for instance, because you have a middleware functionality, well, middleware package somewhere. So how does it work? Does it mean that when I am connected to one node, I have a flow coming from the video server, but the other node, the other adjacent node, knows already that one of them at least knows that this end system is approaching, and the node will ask for the duplicate flow from the server?
Within this particular environment, you've essentially got a limited number of networks that you can actually be on. You've either got a wireless LAN, you've got a physical Ethernet, or you've got some sort of dial-up connection. So that means that it's quite easy to predict what's happening. If you've actually got a physical Ethernet connection, then that's a yes or a no. You've either got it or you haven't. Wireless LAN, you can actually pick up things like signal-to-noise ratio, so you can actually get some indication of what the current signal strength is, what the characteristics of the link actually are, or whether it's worth actually using that as a mechanism to transfer your media. And if all else fails, you've got some sort of dial-up connection which normally works as a last resort. So essentially it's up to the system just to actually drop down at each level onto whatever's left.
I'm just curious, you are covering some areas where it's difficult to get power. Do you think this is a problem for using wavelengths in walking areas or so?
Well, we thought about mounting the base stations in cars and getting people to drive around, but I don't think that's probably going to work too well. It's surprising where you can actually put these things and actually get them to work. There's normally some power of some sort. There are things like street lights. Even in the park that we're looking at covering, there are lamp posts and all these sorts of things that you could imagine getting power from. Also, if you actually approach companies and so on with the idea that they may actually be able to get a wavelength connection around the building, they're normally quite amenable to offering you a little bit of power. Actually, one of the problems that you do get is people basically just not understanding what wireless networking actually is. So you do get a few problems trying to persuade people what the technology is actually capable of and so on. But normally it's not too much of an issue.
Perhaps the last one. In terms of regulation, I don't know how it is in the UK, but I know that in France, you just can't put everywhere or anywhere some wireless system. You said that you were going to provide services in the city center, so you are putting yourself in the position of an operator.
Depends what you're actually doing. If you're actually doing something as a research project and you're not actually providing a commercial service, then that's something you can do. We're not setting ourselves up as someone like BT or something like that.
Are you planning to use UMTS in your architecture here?
As soon as that becomes available, yes. Now there are already plans to do that.
Okay, I think we'll finish on this question. I thank again Andrew, Victor, and don't forget that tomorrow, till my conference,